All right, so the last topic here in kinetics is that of reaction mechanisms. Now, reaction mechanisms are really just a way of putting together two ideas. One of those ideas is that in order to have a chemical reaction that makes sense in context with its rate law, some of those reactions are going to have multiple pieces and parts to them. We briefly talked about the idea of molecularity. The experiment that we did yesterday, or that we were going to do yesterday, that we'll talk about in a little bit, involved this chemical reaction. This was the chemical reaction that we were going to look at. This is called the iodine clock reaction. Now, if this reaction were going to occur all at once, think about it from a collision theory standpoint. How many molecules are there in the reactants? Five, right? I've got two hydrogen ions, two iodide ions, that's four, plus a hydrogen peroxide, there's five. Now, again, from a collision theory standpoint, if all of those are going to come together to make my water and my iodine, I'm talking about five molecules colliding simultaneously with proper energy and proper orientation. How likely does that sound? How hard is it if you're sitting at a pool table and you're trying to get three balls to hit each other at the same time on the pool table and all come together in one confluence? That itself is pretty hard. Sometimes it's hard to get two together, especially if you lack coordination. So just the sheer act of getting all five of them together at the same point sounds almost impossible. Add in that orientation and that energy piece, and we're talking about something that's really, really difficult. And so from that logical standpoint, we have to accept the idea that chemical reactions aren't necessarily going to take place all in one single step. When they do, we call them elementary reactions. And there are some that do. For example, if we have a molecule that is just decomposing, that is going to be an elementary step. It's going to happen all at once because, well, there's nothing else that has to collide with. Or maybe, it has to collide with another molecule of the same kind to get its energy up, to make it second order, whatever the case may be. Or if I'm looking at a synthesis reaction, I've got hydrogen molecule and iodine molecule, and we're making hydrogen iodide. That's good chances though that could easily be elementary. The hydrogen ion, the hydrogen atoms and the iodine atoms just have to collide with each other. But if that's not the case, then what we have to introduce is something called a multi-step mechanism, a multi-step reaction, where to get from reactants to products, it's going to take more than one step to do so. And so that's going to introduce some other terms for us. Let's talk about the easy ones, though. Elementary reactions are relatively simple. We can describe them based upon something called molecularity. Molecularity just being how many molecules are involved in the reaction step. So a unimolecular step would have just one molecule involved. A bimolecular reaction would have two, a trimolecular would have three, or termolecular. Beyond that, we've already kind of discussed, it starts to get kind of fuzzy from there. And as we already discussed, the collision model kind of sets it up that as that molecularity increases, the chances of us getting one of those kinds of collisions decreases. And again, just want you to think about that idea. Think about that pool table. You're just throwing balls on that pool table. How hard is it to get one of those balls to collide with one other, two others, three others at the same time? As we introduce more of those balls, it gets harder and harder to do. Multi-step mechanisms, because they are going to have multiple steps, they're going to introduce something called an intermediate. An intermediate is something that forms throughout the course of a mechanism, but gets used up later on in the mechanism. Intermediates are rarely around long enough for us to actually track and measure their concentrations. We can largely theorize their presence based upon things like spectroscopy or just how they get us to the rate law in question. The important part of a multi-step mechanism, though, is it has to satisfy one very important condition. If I add together all of the steps of my mechanism, I got to get the balanced chemical equation at the end. So everything else has to cancel out. Think about a net ionic equation where we end up adding it together. We've got chlorides on one side and chlorides on the other, and so we know that we can cross them out. Same kind of thing. If I have a mechanism and by the time I add together everything, I see that there's some intermediate on one side and some intermediate on the other, I can cancel them out as well. In order for a mechanism to be valid, at minimum, that condition has to be met. I have to be able to cancel out all the intermediates. We can monitor such reactions using something called a reaction coordinate diagram. What a reaction coordinate diagram does is it shows us energy on the vertical axis and the progress of the reaction on the other. Now, we haven't worked with these before, but we have used some of the terminology that gets associated with them in other contexts. So, for example, when we have a scenario like this, where we can see that there is a clear gap between the reactants and the products are at a higher energy than the reactants. They required energy to get there. You've probably heard this term before, an endothermic reaction. Energy has been taken in to that reaction, and the net result is that the products are at a higher energy than the reactants were. This diagram shows that. It also shows the opposite case, where the reactants start out at a high energy, the products are at a lower energy. The exothermic reaction is the result of that. To put in some other terms that we are familiar with, we can look at, well, what is this right here? This gap between the reactants and the top of that energy hill where we see that first transition state. We just talked about it. We call that activation energy. Now, in a multi-step mechanism, activation energy actually is required multiple times because I need a certain amount of energy to get the reactants into the intermediate state. And I need an additional activation energy, usually a smaller activation energy, to turn that intermediate into our product. Now, transition states, we don't say a whole lot about them. We're not even sure exactly what they look like most of the time. But we can kind of think of them as the highest energy configuration of the reacting species that are coming together. This is usually the whatever conglomerate that is there as the reactant bonds are breaking and the product bonds are forming right before they go back to that intermediate or that final state. And so you've got this state of transition there where we are actively in between that bond breaking and bond forming kind of idea. So when we see diagrams like this, anytime we see a diagram that has multiple hills in it, that lets us know that it is a multi-step mechanism. Each one of those hills represents a different step in the mechanism. So this particular reaction diagram shows a two-step mechanism. A very high energy first step, followed by a lower energy second step. Now, what we haven't talked about yet is how does all this kind of come back to the idea of a rate law? Well, that's the whole reason we have mechanisms in the first place. We need a way to rationalize the difference between the stoichiometry of the reaction and the rate law of the reaction. Remember how we talked about at the very beginning, all of 2 days ago, about this idea that stoichiometry and rate law really don't have a whole lot to do with each other. Now, for elementary reactions, it actually does. And so those times where we have seen that the stoichiometry matched the rate law, that's usually pretty good evidence that we have an elementary reaction, a one-stepper. But if we have a multi-step reaction, the mechanism's going to get more complicated because we have to account for those differences. Again, think about that reaction that we started with. Two iodides, 2 hydrogens, and a hydrogen peroxide, 5 molecules in total. How do we go from there to a rate law that isn't pentamolecular? I'll give you a hint. I know we haven't analyzed the data on it yet, but it's not a 5th order reaction. So how do we go to that spot? And the answer is this. As you might imagine, looking at those rate law, those mechanistic diagrams, some of the steps involved are going to be faster than others. We'll rewind just a couple steps here. There is a clear difference in energy required for step 1 compared to step 2. It would come as no shock to anybody that that first step is a heck of a lot slower than the other ones. In kinetics terms, we call that a rate determining step. The step that is the slowest is also going to be the one that determines the rate law. And the one that is the slowest usually has the most energy barrier to overcome, the highest activation energy. So when we can determine what the rate determining step is, we take the stoichiometry of that step, and that becomes our rate law. And so that's how we can kind of go from, hey, this is a 5th order reaction, 5 reacting molecules. You know what? This is actually a 2nd order reaction. How do I go from 5 reacting molecules to 2? Well, I've got to have a pretty interesting mechanism. And the slowest step of that mechanism has 2 colliding partners in it. That's the one that determines when the reaction is going to proceed and how quickly it's going to proceed. Everything else is theater. Everything else is secondary. By comparison, those reactions are fast. And since they're fast, they're not going to have as big of an impact on the rate. So let's take a look at an example. Here is a proposed mechanism for the reaction between nitrogen dioxide and carbon monoxide to make nitrogen monoxide and carbon dioxide. So this is our balanced chemical equation here on the bottom. If we were going off of this balanced chemical equation, we would assume it is 1st order in nitrogen dioxide, 1st order in carbon monoxide. But that's not the case. If I look at my rate determining step here and looking at the molecularity of that step, that tells me that the rate law is equal to K times the concentration of nitrogen dioxide squared. This reaction is actually 2nd order in nitrogen dioxide and 0 order in carbon monoxide. So it actually doesn't matter how much carbon monoxide is there. It matters how much nitrogen dioxide is there. What are some other things that we can pick out of this? Well, we can also pick out NO3 here, nitrogen trioxide, is formed in one step and disposed of in another. That by definition is an intermediate. So when we see other molecules, and I'll give you a hint, a lot of these molecules are going to be kind of nonsensical based on what we have traditionally told you and taught you about covalent bonding. There's usually some funky looking stuff in these. Doesn't mean that's necessarily wrong. It just isn't something that we've really expressed too much to you usually. And that's why they're intermediates. They're there kind of as a placeholder in between reaction steps to connect the dots for us. So if we have a slow first step, very easy to convert that to a rate law. Just take it as it is. What if our first step isn't a slow step? What if it's like this? Fast and reversible. Well, if I follow the same logic as I did on the first slide, I would end up getting a rate law of R is equal to K times NOBr2 times nitrogen monoxide. Problem with this is that NOBr2, again, it's a molecule that doesn't make a whole lot of sense, because where does that second bromine attach? But it's an intermediate. Remember, these concentrations that we use are initial concentrations when we're figuring out these rate laws. I don't know the initial concentration of that intermediate. I don't even know the concentration of the intermediate as it's forming. I have no real way of measuring it accurately, especially since it's fast. So what do? Well, this is where algebra is going to kick in for us. Since we have reversible steps, and keep this in mind because Tuesday we're going to get into reversible reactions. So stash this one away. It's going to come back again after our weekend break. On the forward side, we have K, which I believe it's K1, is equal to nitrogen monoxide times bromine. The reverse reaction, K-1, is equal to NOBr2. Double check that just to make sure we got it right. We did. Okay, so those are our rates. Forward reaction, reverse reaction. Now here's the thing. The forward reaction and the reverse reaction are the same. It's reversible. They're going at the same rate. So since these two are the same, I can set them equal to each other. K1 times NO times Br2 is equal to K-1 times NOBr2. To get NOBr2 by itself, I just need to divide by K-1. So substituting, this is now K1 over K opposite 1 times nitrogen monoxide times bromine. And so if I substitute that in, that would give me K2 times K1 times K, or divide by K-1 times nitrogen monoxide squared, because I now have NO times NO times bromine. These K2, K1, K negative 1, all of that is going to be a single observed rate constant. So in the end, my observed rate constant, whatever it is, multiplied by nitrogen monoxide squared, multiplied by bromine to the first power, there's my rate law. So with this fast reversible step, this is how I can get to an overall third order kind of reaction. So the stoichiometry says that it should be third order overall, second order in nitrogen monoxide, first order in bromine. The rate law says the same thing. But we know from a molecularity standpoint, a termolecular collision seems kind of unlikely. So this mechanism that was proposed gets us around that particular issue. Gives us a way to explain how we get to that rate law without completely busting up in terms of our rational kind of logic associated with this process. So let's do another example. We've got the decomposition of dinitrogen pentoxide to nitrogen dioxide using these 3 elementary steps. Question is, what is the rate law for the overall reaction? So when we are asked a question like this, the first thing we need to do is we need to find that slow step, that rate determining step. From that rate determining step, we can write a preliminary rate law. There's our preliminary rate law. Now, if that preliminary rate law contains no intermediates, we're good. We stop right there. Since this is an intermediate, however, and the way we can identify it as such is here it is, but it's not one of our products. Now we have to do that same kind of process that we did before. K1 times N2O5 squared is equal to K opposite 1 times N4O10. Solving for N4O10, we get K1 over K opposite 1 times N2O5 squared is equal to N4O10. So substituting that in, R is equal to K2 times K1 over K opposite 1 times N2O5 squared. Remember, this combination of K's would come off as a single rate constant. So that would be the actual rate law, second order in dinitrogen pentoxide. Questions with this example? All right, so I'm looking for two things here. What is the overall net reaction? And what is the rate law for this mechanism? Give you a couple minutes to figure it out, and then we'll talk about it together. All right, so for the first part, just the overall, we're just adding these two equations together. So since there are only two equations, it should be relatively easy to see that the N2O2s are going to cancel out. We'll end up with 2NO plus Br2 makes 2NO Br. So that's the first part. Now, the second part here, we have to focus on that slow step. So the slow step here tells us that our rate should be equal to the value of K2, whatever it is, multiplied by N2O2, multiplied by bromine. Now, the problem there, of course, is that the dinitrogen dioxide, N2O2, is an intermediate. And so we would have to bring in from the previous step the way to get rid of that intermediate. So knowing that K1 times nitrogen monoxide squared would be equal to K minus 1 times N2O2, dividing each side by K minus 1. I'd end up with K1 over K minus 1 times NO squared. And so if I shove that in for N2O2, I end up getting rate is equal to K times nitrogen monoxide squared times bromine. Now, I'm going to let you in on a little hint here, a little trick. That'll probably save you a good bit of time in algebraic angst. If you are encountering a situation like this, where you have an intermediate that is formed in the step immediately above it or in a step immediately above it, if that intermediate is the only product in that reversible reaction, you can just merge the two together. We've seen this now in several examples. The last 2 or 3 examples that we've done basically have been that. We take whatever's in that equation above and we drop it in the place of that intermediate below. So if that's what you're encountering, go for it. It'll save you a little bit of time, a little bit of trouble. Now, you shouldn't see too many examples like this, but if there was a secondary product in there that was also an intermediate, you couldn't simply do that. You'd have to work your way through it. Fortunately for you, that's a 300 level kind of kinetics problem. That's a graduate level kind of kinetics problem, even in some cases. when I took chemical kinetics in graduate school. That was the kind of stuff we were doing, was multiple intermediates and using different approximations to try to get that rate law to come out correctly. We're not asking you to do that in a 100 level general chemistry course. Chances are pretty good if you have an intermediate in your rate law, you're going to find the answer to it in the mechanism step right above it. And if not right above it, then the one right above that. So if that's the case, merge. Merge the step that has the intermediate as the product into the rate determining step. That should give you the rate law. All right. Any questions on this before we put it away? Okay. Just some last concepts that kind of clear this deck for us. Catalysts. Now, up until this point in time, we've only talked about a catalyst as being that thing that speeds up reactions. Now that we have a little bit of mechanism behind us, we can explain better how that happens. Because what a catalyst does is it creates an alternative mechanism, a different pathway for the reaction to proceed in. And in that different pathway, you end up having a rate determining step that has a lower activation energy. And since it has a lower activation energy, it's going to go faster because it doesn't need to be amped up to a higher temperature. Now, when it comes to catalysts, there are two types. There are the homogeneous catalysts. Those are the ones that are in the same phase as the reaction mixture. A good example of those are solution-based catalysts that you would add to a reaction in solution. Not to beat on the drum too much, but that would have been the type of catalyst we would have used yesterday in that peroxide lab to speed up those reactions. And then there are heterogeneous catalysts. Those that are in a different phase, those are the ones that depend more on surface area and those kinds of things. We talked about them kind of at the beginning of Wednesday, things like the catalytic converter in your car, where you've got that piece of metal that is spread out over a large surface area so that it can maximize its catalytic power. From a reaction pathways kind of standpoint, this is the reaction that we were looking at largely yesterday. The only difference is that we were looking at iodine instead of bromine because iodine's a little bit safer than bromine is. But the idea is essentially the same. If I'm just looking at the thermal decomposition of hydrogen peroxide, that reaction is going to be relatively large in the amount of energy it takes to do. But if I introduce bromide and hydrogen ion as catalysts, so we have the catalyst in there, we're keeping it at a certain pH to stabilize it, we can see that the net result is a reaction that has a much lower activation energy and therefore would go faster. And you can actually look at this and see which one of these two is the rate determining step. It's the second one. Second one has the biggest energy hill. All right, just for some fun here, let's take a look at a couple of examples of these in action. So for homogeneous catalyst, So what's going on in that one, that is the iodine catalyzed reaction of hydrogen peroxide to make water and oxygen. So just like the reaction that we saw on the previous slide with the diagrams. What makes it all frothy is they add a good deal of soap solution to it. And so what happens is the soap bubbles will capture those oxygens as they are forming and trap some of the heat. And that's why it steams up a little bit as it goes too. The heat of the reaction actually gets trapped, and we start to see some of that water turn into vapor as it is coming out of there. But the reaction itself happens so quickly, and that's why you get that big foaming up effect. You're getting lots of oxygen being generated in a very short amount of time in a very condensed cylinder. This other one with heterogeneous catalysts.
So this demonstration is the platinum catalyzed oxidation of methanol, and it is an oscillating flame reaction. So into a large Erlenmeyer flask, I pour about half a cup of methanol. This is the platinum wire catalyst. If I drop it in as is, nothing happens. The platinum has to be activated with heat, and with our traditional heat source, MAP gas torch. Now I'm going to turn off the lights and let it load and record.
So what you have here is actually an example of something called flameless combustion. So the energy of the flame is not enough to actually get that wire to glow, and not only glow, but continue to get brighter and brighter and brighter up until the moment of ignition. What's happening is as oxygen is coming into the flask, it is burning the methanol in there, but it's not burning at a high enough concentration for us to actually see flame and heat and light. But it is giving off energy. That energy is being absorbed by the wire, which is providing activation energy enough so that when enough oxygen is able to replace what was combusted, it'll flame up again. And so what that platinum wire is doing is it's basically providing a place where the oxygen and the methanol vapor can commingle to do its reaction. So that's our examples there. There are biological applications of catalysis as well. In relatively simple terms, that's what enzymes are. They are biological catalysts of some kind. Now they work differently in the sense that the method of operation that they have, the fact that they have an active site, does make things a little bit different. They're not quite the same as what we think of as chemical catalysts, but their job is similar. They will help to make a reaction take place, and it'll happen at a lower energy, lower activation energy than what it would take for those two things to come together on their own.